When we look up at the night sky, we can't help but feel overwhelmed and small in the face of the vast universe. This stems from a much deeper and more astonishing truth. Our universe appears to be so incredibly finely tuned that it's almost unbelievable, just so life can emerge and exist. The laws of physics, the fundamental constants of nature, and the initial state of the universe appear to be exquisitely balanced to a razor's edge of precision. Just a small change in any of these factors, and the universe would transform into an entirely different place, empty and lifeless. This is not just an empty academic statement, but a conclusion drawn from the most meticulous analyses in the fields of theoretical physics and cosmology. This issue, known as the fine-tuning problem, is one of the greatest and most hotly debated mysteries in modern science. This compels us to confront the most fundamental questions. Could our universe merely be an unbelievably lucky outcome in an endless cosmic lottery? Could our very existence be proof of a deeper order, an inevitable mathematical law, or even a preordained design? To begin this journey of unraveling mysteries, we won't start with abstract questions, but dive straight into the foundation of reality, the fundamental building blocks that shape our worldview, natural laws and constants. Every phenomenon in the universe, from a falling apple to a supernova explosion, is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The harmony and emotional bonds among people is the most essential condition for our existence. 1. The strong nuclear force is one of the four fundamental forces of nature, responsible for binding protons and neutrons together in the atomic nucleus. This is the strongest of the four fundamental forces, but it only operates at an extremely small scale within the atomic nucleus. Its role is to bind protons and neutrons together while counteracting the powerful electrostatic repulsion between positively charged protons. Here are two natural English translations of the given Vietnamese text. The nucleus of every element, except hydrogen, the simplest element with just one proton, cannot exist without neutrons. If not for heavy elements like carbon, oxygen, or iron, essential components that form rocky planets and sustain life, the universe would be nothing more than a sparse cloud of pure hydrogen. If the strong nuclear force were just 2% stronger, another catastrophe would occur. The gravitational pull would then be so immense that protons could easily fuse together. Shortly after the Big Bang, nearly all the hydrogen in the universe fused to form heavier nuclei, primarily deuterons, d-protons, nuclei consisting of two protons bound together. This would burn up all the hydrogen fuel in the universe from its earliest days. Stars that last billions of years, like our Sun, which slowly burns hydrogen to produce energy, would never form. No stars mean no light, no energy source to sustain life. The strength of the strong nuclear force lies within a narrow range that is just right, ensuring hydrogen is abundant in the universe while allowing heavier elements to form within stars. 2. The weak nuclear force, as its name suggests, is significantly weaker in strength compared to the strong force and electromagnetic force. This force only operates at the subatomic level and plays a crucial role in radioactive decay processes. Its role may be modest but is incredibly vital. The weak force enables neutrons to transform into protons and vice versa. This process plays an essential role in nuclear fusion reactions within stars. Inside the Sun, two protons collide, and through the action of the weak force, one proton transforms into a neutron, forming a deuterium nucleus, an isotope of hydrogen. This is the first step in the fusion reaction chain, the process that generates the energy sustaining the Sun's activity. If the force were slightly weaker, this reaction would occur too slowly for stars like the Sun to shine. Conversely, if it were slightly stronger, the reaction would happen too quickly. The stars will burn through their fuel and die out too soon, leaving complex life insufficient time to evolve on the planets orbiting them. Moreover, when massive stars exhaust their fuel and collapse, the very weakening of gravitational force triggers a supernova explosion. This explosion not only creates elements heavier than iron but also scatters them into space, sowing the seeds for future generations of stars and planets. If not for the weak force, the elements that make up humans and Earth would forever remain trapped in the cores of dead stars. 3. Electromagnetic force. This force governs the interaction between charged particles. It keeps electrons orbiting the atomic nucleus, contributing to the stable structure of the atom. It binds atoms together to form molecules, from simple water molecules to complex DNA strands. Every chemical structure, every biological process, and nearly everything we see or interact with daily is formed by the force of electrons. The issue here lies in the ratio between electromagnetic force and gravitational force. The electromagnetic force is approximately 10 to the power of 36 times stronger than gravity, an astronomically large number. If this ratio changed even slightly, the universe would be entirely different. If gravity were stronger or the electromagnetic force weaker, stars would become smaller, denser, and have much shorter lifespans. They will burn through their fuel in just a few million years, a span too brief for intelligent life to evolve. Conversely, if gravity were weaker, stars would not reach sufficient core temperatures to initiate nuclear fusion, or they would become overly massive and disperse, preventing the formation of stable planetary systems. 4. Gravitational force. Though the weakest of forces, gravity has an infinite range and is always attractive. It is the great architect of the universe on the largest scale, drawing matter together to form stars, galaxies, and even superclusters of galaxies. 5. The evolution of gravity is closely linked to the expansion of the universe. After the colossal explosion, a fierce tug-of-war ensued between the outward thrust of the early expansion and the inward pull of gravitational forces. If the initial expansion rate had been just slightly slower, by about 1 part in 100 quadrillion, gravity would have prevailed and caused the universe to collapse back into a big crunch, even before galaxies had a chance to form. If the expansion rate of the universe were just slightly faster, matter would disperse too quickly for gravity to pull it together and form stars and galaxies. In that case, the universe would become a cold, dark, and nearly empty space. This balance is like throwing a ball upward with just the right speed, enough to escape Earth's gravity but not so fast that it flies away. Beyond those 4 fundamental forces, there are other numbers and conditions that also exhibit astonishing precision. 1. The cosmological constant. This is perhaps the most striking example of fine-tuning. The cosmological constant, often associated with dark energy, is a form of intrinsic energy of space that causes the universe to expand at an accelerating rate. Physicists can calculate the natural or predicted value of this constant based on quantum theories. However, the measured value from astronomical observations is significantly smaller than the theoretical prediction. The discrepancy amounts to about 10 to the power of 120 times, an almost unimaginable number. This is the greatest difference between theory and experiment in the history of science. If the cosmological constant were close to the value predicted by theory, its repulsive force would be so immense that it could tear the universe apart from its earliest moments. Matter would never come together. At that point, the universe would have no galaxies, stars, or planets at all. Our existence requires this number to be extremely small, nearly zero but not completely vanishing. The fact that it holds such an infinitesimally tiny positive value remains a profound mystery. 2. The process of carbon formation. The story of the carbon element's journey is particularly famous. Carbon is the foundation of life on Earth. This element is formed inside stars through a nuclear fusion process called the triple alpha reaction, where 3 helium nuclei combine together. However, this process is nearly impossible because the probability of 3 particles colliding simultaneously is extremely low. In 1952, astronomer Fritz Zwicky discovered that for the universe to contain sufficient carbon, there must be a special resonant energy state within the carbon-12 atomic nucleus. This state will act as a buffer, helping to keep the 2 helium particles bound together long enough for a third particle to join in. Based on the essential needs of life, Hoy accurately predicted the existence and energy level of this resonant state. Later, experimentalists at Caltech confirmed its existence, perfectly matching Hoy's earlier prediction. This coincidence is a subtle adjustment in the laws of nuclear physics, creating an element essential for life. How should we act in the face of clear evidence that the universe is remarkably and finely tuned?